Swayam Prabha. Digital India. Educated India.
Now we want to move to continuous time Markov chains. So far we studied discrete time Markov chains. When we studied discrete time, time was discrete, right? Like we allowed n equals to 1, n equals to 2 like this. So we only looked for the change in the Markov chain at specific discrete times. And we had allowed ourselves to look only into some countable set of states, and that's why we called it a chain, because we have certain states going from one state to another states, like it is kind of forming a chain there. So that's why we studied so far discrete time Markov chains. But now I don't want to look at the things at particular time instances, but maybe I may want to look at my process continuously. And now I want to now study what is the Markov property on such a continuous time. We have defined what is a Markov property, what is a Markov chain when my time is my time is discrete. Now we want to go and see how we are going to deal with the case where my time is not discretely indexed, but it's a continuous random variable. We already know what is a continuous random process. Continuous random process is nothing but a sequence of random variables indexed continuously, right, at every time. Now we want to understand what is continuous time Markov chain. Okay. So definition. Process. So as usual, we are going to always assume that this state space S is discrete. So what it is saying, the probability that you are interested in knowing your process takes value state j at time t plus s, given your process all the way up to s. What is this is telling? So this condition here tells that you have been told what is your process till time s, and now you are interested in knowing, okay, what is the probability that in further t second, further t more time, that is s plus t, that you are going to take state j. What is this probability? Okay. So like this, your process is taking value over continuously. This is s, and let's say this is t. So your process is taking continuously value, and you have been given what is your process all the way up to time t, and now from this you want to know what is the value your process is going to take at time s plus t here. This process, this probability only depends on the value your process has taken at time s. I really didn't care about all this before time s. Only if you are going to look something beyond s, I only need to know what has happened at time s. And this is what this is telling. This is same as what we did it in the Markov chain, right? So there we have said that okay, the future depends only on the current state, and I don't care about my past. Here it is also saying the same thing. Okay, past I don't care, just tell me what is going to be happening at the current. But now it is just extension to the continuous time version. Here t and s both are continuous valued. Okay, so we have already seen some processes, right? Continuously indexed. What is such a one process? Okay, renewal process where what was MT, right? MT was continuously evolving. And what would you say that MT is distributed how? We just said that it is distributed Poisson with rate lambda t, right? Like what was so what would you say? Yeah, Poisson process. But for general process, did we say anything like if you have a renewal process UIs with certain mean value, what is MT is going to look like? So fine. So we had specifically mentioned about my Poisson process. By the way, is Poisson process is a continuous time process? How did you define a Poisson process? Poisson process is a counting process, we said, right? And it is going to give the number of arrivals or number of some events happening till time t. So there also it was a sequence of continuously indexed random variable. Okay, fine. Let's say now if this Poisson process is a CTMC. Okay, Poisson process is a continuous time random process. We want to see whether it satisfies this definition. Okay, let's say NT is a Poisson process with rate lambda. So we know that at any time t, this NT is what? NT is the number of arrivals or lives that has occurred in the interval 0 to t. So all these values are integer valued numbers. N of t is, this is a counting process, right? So every time it is going to count how many times things have happened in the interval 0 to t. So n of t is going to take value 0, 1, 2, 3 like that. Now whether if I am going to ask the question, okay, number of renewals or number of arrivals till time t plus s given till this, does it depend only on n of s, not all u less than or equals to s? and for specifically let's assume that n of s is equals to some I. So when I said this n of u given n of u less than or equals to s means I have described you my process all the way up to s. When I said I have described my process till s, I have told you what are the states that has been taken by this process till time s. Okay, so let's say at time s it has taken a particular state I, and now I want to see that whether this probability, it only depends on what is the state taken as s and does not depend on what has happened before it. Okay, is that true? Okay, so let's say, and that is true, right? Like, because what has happened till s, and I'm just counting, so my counting accumulates. After that point I'm only going to see what more has come. So let's write that in a formal way. So this is the intuitive idea, but we have to bring in the definition of my Poisson process to argue this. So instead of asking this question, nt plus s going to j with n of s equals to I am asking that, okay, the number of increment that has happened between the interval t plus s to s is j minus I. So it is the same thing, right? Like instead of going directly from I to j at time t plus 1, it is I am asking that between s and t plus s interval j minus I renewals have happened. And with this we are done, right? What is the property of a Poisson process? Poisson process has independent increment. So what is this is saying? This so far this is saying that, okay, this is like the number of arrivals in the interval 0 to s is I, and this is the number of arrivals that has happened between s to t plus s. So the interval here is s to t plus 1 and here the interval is 0 to s, and these are independent events. This is nothing but probability equals to j minus I, and here I, so this is, I have assumed that n of s is already known to me. So you already see that you have eliminated dependency of this probability on all the things that has happened before time s, and this you can just now go and do the reverse process. Then this is saying, okay, this is equal to j given, yeah, this is still n s equals to I, and then you are done. So by definition of the Poisson process, you already have this condition. So what is the crucial point you use? You wanted to make sure that the increments in disjoint intervals are independent. If they are not, you don't know it, right? So, okay, let's say something has happened in this interval, and the amount of the increment that is going to happen in the next some interval is going to depend on what has happened in the previous interval. Then they are not independent, right? Then in that case, I actually needed to know what has happened before I can say what is the probability that this is going to happen in this interval. So there is no Markov property there. But in the Poisson process, given that like this increments in disjoint intervals are independent, this allows us to make sure that I don't need to know before what happened to say what is happening in this current interval. Okay, so that's fine. Now most of the things now we are going to do next is very similar to what we did for the DTMC. Like when we started with DTMC, we defined what is my transition probability matrix, how I define what is my one-step transition probability matrix. Then we said how I'm going to write my joint finite time distributions in terms of my this transition probability matrix. So let's see how we can do all the things for my continuous time Markov chains. So first of all, we are going to, for simplicity, we are going to assume time homogeneity like the other, like in the DTMC. We are going to assume that so if you are asking the question, okay, at time s you are in state I, and what is the probability that you go to state j at time t plus s. So here you are looking for an interval s to s plus t, right? So its length is simply t. We are going to assume that this probabilities only depend on that length of the interval, not exactly from the point where you started. Okay, so it does not matter where you are going to start. What matters here in this probability is what is the length of that duration. This is, we are just going to call it time homogeneity. It does not matter which s you are going to put, as long as the length of that interval is same. It is going to be governed by the same probability. Now we are going to denote by this p of t is equals to pij of t. So all this collection of probabilities for every state I and j for a given t, I am going to denote it by p of t. So is my p of t is a stochastic matrix? My p of capital P of t, it is going to stochastic matrix, right? All the row is going to sum to 1. And we are going to, like on the earlier case, we are going to define p of 0 to be I, identity matrix. At time t, we are going to assume that in 0 times you are going to be just falling back in your own state, not you are going to move to any other state. So that's why only diagonals will all be 1, others are going to be 0. And then this we are going to skip, but you can verify that if I have transition probability matrix for time t plus s, this can be written as p of t and p of s. So this is in a similar way what we did for TTMC, where we could split my transition probability matrix for a sum of 2 discrete times into that of individual times. So we are just doing the same thing here. So it follows the same steps there, just skipping this. Okay, now here is the contrast. Let's contrast. In our DTMC, we had written P of n. What is P of n? P of n there in the case of DTMC is the n step transition probability matrix. That we had written in terms of one step transition probability matrix by raising it to the power n. So now is such a similar analogy holds for CTMC. So what is the meaning of n here? N steps. When you are going to take t here, what is the interpretation in CTMC? It is like interval of length t. There you will be interested in transition at every instance, right? When you are looking at n, you are looked at n time steps, but in time, even in some interval 0 to t, you will be interested in transition at every instant. That means it has infinitely many, uncountably many transitions possible in that. So that does not make sense. Like I am going to write p of t to p to the p for this p to the power capital T, or like. So even it is not clear like how to define a one step transition probability here. right? Like my translation can happen at any instance starting from 0. So that does not make sense to represent my translation probabilities matrix here in terms of one-step translation probability matrix. So earlier in a DTMC, for a time homogeneous case, it made sense to give my n-step translation probability, everything in terms of one-step translation probability. But when you move to CTMC, you have to specify my translation probability matrix for every t. Okay. So in CTMC, I need to know this P of t for all t greater than or equals to t. We will see that. Okay. Why it has to be of that form, not anything else. So P of t plus 1, we are saying that it is going to split. So is that exponential is the only one which will have this property? Is that the case? T plus delta t, whatever, like you just define S as delta t. Okay, so we will see a bit in a couple of minutes that it is indeed true that this distribution is going to be exponential distribution, but not in on this what in this, like here it is clear, but we will sit in a different setting and then we'll again revisit it, but whether this P of t has to be exponential again. So I said I have skipped this. You have to go and use the same steps as we did it in DTMC case. Okay, there also we had split right. There we did it for any n1 plus n2. We had said this is going to be P of n1 into P of n2. You have to just do it like. So here just like split this probabilities conditioning on two parts and just apply the Markov property that you are going to get. Okay, fine. So this PT here, that's why you are going to call it as transition probability function. Because it has to be specified for every t. So every t it's a matrix. We are just going to call it as translation probability function. Now you can verify that. Simply I am going to write this finite dimensional distributions for this. So we'll see that this can be just like after applying the Markov property 0 I1 T1 I1 I2 T2 I2 Y minus 1. And if you further write it as x naught equals to I, this is your initial distributions. The same thing you could write it as no, not unconditional one. Okay. So this is the conditional joint distribution, right? So you are looking at your CTMC taking value I1 at time t1, I2 at time t2 and In at time t1. Given that initially it started with state I0, you could simply split it like this, just apply the Markov property repeatedly, then this probability is nothing but probability that you go from state I0 and I1 in time t1, and then probability that you go from state I1 and I2 in time t2 minus t1 similarly. But this is like a conditional distribution. But now if you are interested in this, simply the joint distribution, and which we call finite dimensional distribution FDDs. So now for this you could just bring in just unconditional it over your initial value. So if you know your initial value, you could write this. So we always said, like, to complete the characterization of your process, you need to give full description of your finite dimensional distributions, right? So to give finite dimensional distribution for the DTMC, what all the things we said we needed? Right, we said we need a one step transition probability matrix and your initial distributions. So here also, what all the things you need to give a complete description of your process? You need to give your initial distribution, and then you need to give your transition probability function here. Okay. So far what we have been doing is, we have a continuous time Markov chain. We have described about its Markov property and how to write down its finite dimensional distributions. Now in a CTMC, once you are going to hit a state, you are continuously watching it, right? At every instant you are watching your random process. You want to know how much time my process is going to stay in that state before it jumps to a new state. Like if it is a CTMC, it must be the case that, okay, it hit some state, maybe stayed in that state for some time, and then went to a new state and stayed it on that state for some time, and then moved to another state. Or it may be such a very shaky random process that it is not staying in any state for any good amount of time. It came to one state, immediately switched to another state, and it can be very like unstable thing, like it is not spending any time in any state for a longer time. But you want to capture this, okay? So this is anyway continuous time process, like I'm watching it continuously. So in the discrete times, you only worried about your Markov chain at particular instances. But here I have to now completely describe how it is behaving at every time instance. Maybe one way to describe that is just give an alternative characterization by saying that if I hit this state, if I'm at this state at particular time, I'm going to stay in this state for this much more time. Maybe that's a random value, but if you can give that distribution, maybe you can alternatively characterize your continuous time Markov chain, right? So that those are all can be given through your sojourn times. Sojourn time in a So sojourn time is the amount of time you are going to spend in a state before you move out of it. Okay. So we are going to define at any time t So can you parse it, what's happening here? So okay, I am defining this function y of t for any given time t. What I am looking is, I am looking let's say x of t is any state at time t. Now I am looking for t of s. So t of s will take some state, right? Like this is the state taken at time t of s. I am looking for s from time t in which it is going to take a time going to take a state other than xt. And what I am looking at, I am going to look for an s which is the smallest among all of them. So I am going to look for the time that, yeah, so the time I am going to live, I am going to stay in that state, right? And basically I am here when I check this condition, I am looking when I actually left my state. So when I said t, I don't care in which state I am, whatever that state is, xt, let's some random state. What I am just looked is how long I stayed in that state, and I am just looking at the minimum amount of time that is required. And this could be a random quantity, right? Because both x of t and x of t plus s themselves are a random quantity. And this is what we are going to call it as a sojourn time. So sojourn time is basically the minimum amount of time you are going to spend on a particular on a state at that time, at a time t. So this is defined for every t. So you look for a process at some time t, you just see when is the earliest that it is going to change its state. That is going to give you a sojourn time. Now comes this theorem. So what it is saying is, okay, can you see TMC? Let's focus on a particular state I, and at time t. You have given that at time t, you are in a particular state I. Now what have been asked is the probability that yt is greater than u. What is yt greater than u means? The probability that it is going to stay in that state I for at least u more units. Okay? At least u more units going to be e to the power ai u for some ai which is a positive real number. So what is the distribution of yt? Conditional on xt equals to I, then it is going to be exponentially distributed with some ai which is function of that state which your process has taken at time t. Okay, so if you realize that, so okay, fine. So these AIs, let's say for every I have these AIs. Once you know what is your state space, you have for all i's, you know AIs. And let's say at time arbitrary time t, you realize that you are in particular state I. Okay, now the amount of time that it is going to continue to stay in that same state is exactly going to happen according to this distribution, which is now exponentially distributed with parameter what? This parameter ai. So in a way what we are saying is, if your continuous time process has this Markovian property, it must be the case that the amount of time it is going to stay in a particular state at any arbitrary time is also memoryless. Exponential distribution, we know it is a memoryless property, right? So what is Markovian property? Markovian property in a way like I don't care what has happened before it, what matters is my current state. After it is only going to govern next thing. In a way there, it is also given the current state, it does not depend on anything which has happened before, right? So for that, in a way like we won't be surprised with such a result that if you already know that you are going to be in a particular state at time t, it must be the case that the amount of time you are going to spend in that state is again exponentially distributed. So fine. So let's quickly go through the arguments. Okay, so let me define these quantities here. I am interested in probability that x of s equals to I and t. So I am going to define this probability as that given that I am in state I at time t, that I continue to stay in that state I in the interval t to t plus u plus v. Okay, so alternatively this is nothing but saying okay, I am in this interval. I was already in state I at time t, I will continue to stay in that state in this interval. So this one you can simply expand it again by chain rule. So for this probability I just applied chain rule. I split this interval t to t u plus v to t plus u, and then t plus u to t plus u plus v. So I have just split my total time between t to t plus u plus v into this part t plus u, and then now by definition what I am looking at, like given xt equals to I am now asking the question, okay, x of s that I am going to stay in the same state I in this interval starting from t to again t plus u. According to this definition, this is nothing but g of u, right? Earlier it was for g of u, but now I split it is only over the interval g of u. And what is this other part now? For this other part I am going to again apply my Markov property. From Markov property I know that actually I have already applied my Markov property, and I already know that my x of s is I in the interval t to t plus u, and I don't care what has happened before that. So I already know at x of s I have going to I, and now I am asking the question, okay, what is the probability that it is going to continue to stay in the state I again? And now what is the length of this interval? It is going to be v. So it must be the case that this is g of v. So this probability I could split it like this, and as one of you said, like it is only the property of the exponential distribution that I could do this. So it must be the case that this probability here that I am going to stay. So okay, so what we just showed is g of ti is equals to e to the power phi t for some I don't know what. So what we have basically said is, given that I am in state equals to I, the amount of time I am going to continue to stay in that is again exponentially distributed, and that's why I am going to get it. But you see that, okay fine, this is the distribution of the amount of time you are going to continue in the same stream you are looking at end. But what is this here? What is this probabilities here and why we could split it like this? So what is Pt plus S? It is the probability that given some state at time 0, that you are going to take some other state at time t plus s, right? And that time I'm going to express it as product of these two terms. Do you feel that it should be also like the only possibility that this can happen is if all this my probabilities, so here they are probabilities, they are all going to be exponentially distributed. So okay, what is the definition of this? Gi of t is like, this is amount of time I'm going to continue to stay in state I again for t more times, right? Like this is let's say this is going to, okay, this I here is the your initial state. Let's say, let's put this is equals to t equals to 0 here, and let me make this is equals to t. Then I will be just looking at 0 to t in this interval, and this is going to be this. So the amount of time I have spent is going to be this much distribution. Then is it not exactly the thing what I'm asking for? Okay, fine. So this is the step. You need to check that exponential is the only distribution that can be split like this. That is what I said, like from that property we are going to use this. So how we are going to do this? You have already not come across this? Okay, so fine. So how we are going to do this? It requires us couple of steps. So maybe like you guys need to figure it out how we are going to do this, or we will just put it as an assignment question. Okay, is it the case? That's what we try to argue, right? What is the interpretation of a P there, and what is the interpretation of G here? So okay, fine. So there are two things. You need to convince that it's not really necessary that my each of these Pij's here in this matrix has to be necessarily like exponential, or like is it the case that that is the only way? So now if you are going to use this argument that the sum has split, if you could split it like this, if exponential is the only possible distribution, why is that not necessarily be here, or it is the only case? Okay, so let's check that. Then here is Pij or exponential. So okay, so let's stop here.